Our next speaker is Jeremy N. Butkovich. Thank you. Jeremy Butkovich, P-E-G-E, is an associate geotechnical engineer for Shannon Wilson, a geotechnical engineering consulting firm based in Seattle, Washington. For the past 15 years, Jeremy has worked extensively on seismic analysis and design of large infrastructure projects, including the Alaska Way Viaduct and seawall replacement project in Seattle, Washington, the Evergreen Point floating bridge replacement in Washington State, and the Port Mann Bridge replacement in British Columbia. Jeremy's areas of expertise include numerical modeling of liquefaction and ground improvement, nonlinear site response analysis, and soil structure interaction. And Jeremy will be speaking on the seismic isolation design of the SR 520 West Approach Bridge. So let's welcome Jeremy.
Good afternoon, everyone. Similar to Sam, this is a project that's taken up a good chunk of my life and my career, and similar to Sam, I think it will continue to do so for the next 4 or 5, 10 years. We'll see how it goes. But this particular phase, we actually got to see all the way through design and then all the way through construction. So that's very exciting to have had that happen. So this is the West Approach Bridge of State Route 520. So this is one of 2 floating bridges that crosses Lake Washington to the east of Seattle, the northernmost of those bridges. And the Washington State Department of Transportation has been busy basically renovating the entire corridor from I-405 on the east to I-5 on the west, moving sequentially from east to west. So what you see in this photo is actually the old floating bridge and the old West Approach Bridge, which is shown down and to the left. And this was built in the early 1960s when we didn't quite understand just how big the seismic hazard was here in western Washington. And so it was basically hollow concrete columns. They didn't extend very far down into the underlying ground. So it was structurally deficient, and the WashDOT decided that it had to be replaced. Now, because this is one of only 2 bridges that cross Lake Washington, WashDOT declared this an essential bridge, which means that after a 1,000-year design-level earthquake, it had to be fully functional within a matter of hours. So what does that mean practically? It means that we have to be able to design the shafts and columns to remain elastic, so no damage after that design-level earthquake. And unfortunately, that meant that standard design methods led to unrealistically large and non-economical bridge foundations. The solution that the structural engineer, HDR, came up with was to base isolate the bridge. And in order to do that, we, Shannon and Wilson, were called upon to perform dynamic soil structure interaction analyses along with HDR and a peer reviewer to design that bridge. So let's get a little bit into this. So here's the location of the bridge, again, Lake Washington to the east of Seattle. And there's the West Approach Bridge north. I say north because there's also a south bridge, a companion bridge that is actually getting ready to go into construction soon. The West Approach Bridge north itself is about 6,000 feet long, contains about 34 bridge piers and a total of 99 drilled shaft foundations. The bridge passes through a very environmentally sensitive area. All these areas near the University of Washington are old wetlands, good for migrating birds and canoers, kayakers, all that kind of stuff. Very shallow water, so that made actually constructing this bridge rather difficult. You couldn't just bring barges in like they did in the 1960s. Dredging through there is not very practical. So they actually had to build an approach trestle, a construction trestle, in order to construct the bridge. Now, under the ground, like most areas in Seattle, the subsurface conditions in this area are controlled by the glaciation that's occurred over the past about 10,000 years ago. Glaciers repeatedly came in from the north and left kind of a grooved north-south trending ridges and valleys throughout the Puget lowland. And those ridges are what you see as the tops of hills in the lowland. And those valleys typically became submerged in water, and then soft sediments, clays, and peat accumulated there. And so as you see down below, we have anywhere from 20 to 80 feet of peat, 20 to 80 feet of soft clay, and then very dense, hard, glacially consolidated sediment that we would use to bear our foundations in. Now, to actually evaluate these subsurface conditions, we performed about 110 soil borings. About 90 of those were over water. The deepest boring extended about 210 feet below the mudline. And we also had to do a really good job of understanding the groundwater regime there. There's actually artesian pressures in the deeper soil, which could lead to issues when you're constructing your drilled shafts. So we installed 21 vibrating wire piezometers in 7 different locations. We had some stacked VWP installations and performed a whole slew of soil index testing, laboratory testing, which included triaxial tests and also some dynamic testing, a bunch of field testing from CPTs to vane shears, shear wave velocity tests, pressure meter tests, the whole gamut. So this was the preliminary bridge design that we set about to optimize using our dynamic soil structure interaction analysis. As I mentioned, there were about 3 to 5 bridge columns per pier, so a total of 99 drilled shafts. Now, those drilled shafts were about 8 to 12 feet in diameter, and as I said, they extended to about 120 feet below the mud line. On top of those bridge columns was a cross beam, and that's where the seismic isolation bearings were placed. The seismic isolation bearing selected for this particular project is what's called a triple friction pendulum. You can imagine 2 dish plates kind of on top of each other with a little baseball in between them. That's kind of the rough schematic for how those move about. So WSDOT policy states that we need to have a peer review of any dynamic soil structure interaction analysis. So the first model was our design model, and the second one I'll show you is the peer-reviewed model. So the design model was done in CSI Bridge by HDR. And because of limitations with that particular program, they had to design the superstructure and substructure separately. So we performed a series of soil structure interaction analyses looking at the drilled shaft and got displacements at the top of those shafts. And I'm making it break. There we go. Got displacement time histories, and then we also got stiffness matrices at the top of those shafts. Gave those to HDR, and they were able to combine them into their model and then run those analyses. Boy, the computer really hates my animation. Okay. Peer review model was more of a standard soil structure interaction analysis that's typically performed. We provided soil springs and displacements up and down different locations of each shaft using a total stress site response analysis, and then provided those to the peer review structural engineer, who then ran that through their ADINA model. A lot of detail there, but I only have so much time. The big thing that I want to impress upon you, and that was rather unique about this particular project, was how we dealt with Western Washington's unique seismic setting. So the seismic hazard in Western Washington is pretty much driven by the subduction of the Juan de Fuca plate beneath the North America plate, and that leads to 3 major types of seismic zones. So here's the 520 bridge. The first are shallow crustal faults, similar, they could be the Seattle Fault Zone or the Southern Whidbey Island Fault Zone. The second, which isn't pictured here, are deep intraplate earthquakes, similar to the 2001 Nisqually earthquake that happened out here. And the third and scariest is the Cascadia subduction zone. These are magnitude 9 earthquakes, similar to what we saw in Tohoku, Japan, back in 2011. To further complicate things, these crustal faults also form a sedimentary basin called the Seattle Basin. I won't get into any details, but suffice it to say, we were able to capture some of those effects, and that's become a very big deal for design of tall buildings in Seattle. So from a deaggregation point of view, these are the 3 major sources, and you can see they all have very different magnitudes and distances to the site. How much time do I have? Oh, thank you. So in order to design the bridge, we need a uniform hazard spectrum. And what that is kind of a conglomeration of all the different possible earthquakes that could affect a site. They're all put in a blender, spit out in a very average way. So this uniform hazard spectrum is not representative of any one particular earthquake, and that's very important to note. So in order to, let me back up for a second. Typically, we would match time histories to this spectrum for use in an analysis. But when you match these time histories to this spectrum, you can end up with very unrealistic levels of shaking, again, because this particular spectrum is not representative of any one actual earthquake. So to get around that, we use a technique called conditional mean spectra. This is a statistically rigorous way to develop more realistic time histories based on the actual type of earthquake source that we expect will affect the site. In order to do a conditional mean spectra, we need to know a little bit about the structure itself. in particular what its period range of interest is. For the West Approach Bridge North, we had two period ranges of interest. One was this very long period here, which I'll highlight. The other is a shorter period, which you'll see momentarily. And so when we applied this conditional mean spectra technique to the uniform hazard spectrum, instead of using that red line to match to, now we can actually match to this black line. And you don't need to be a seismic expert to see that that's a pretty significant reduction in your demands. And you might ask me, well, Jeremy, how can you do that? That you're just reducing your demands willy-nilly. And actually, no, we're not. Like I said, this is statistically rigorous, and this is actually more representative of what would happen during a magnitude 9 type earthquake. This design spectrum is basically what a magnitude 9 type earthquake would give, but where it would also just be able to match the bridge in that period range of interest. Similarly, we can do that for a shallow crustal earthquake, say a Seattle fault rupture, and that would look something like that. And then for our second period range of interest, which is the shorter periods, we also looked at a crustal conditional mean spectrum there. So the upshot, looking at it in terms of displacement versus time, if you match a time history to the uniform hazard spectrum up top, you can see we get a peak displacement of about 80 centimeters. Whereas if you match to the conditional mean spectrum, you get a displacement on the order of 30 to 40 centimeters. So more than twice reduced. So you can understand how very quickly this leads to a much more economical design, and I'll show that here with the moment response with depth for a representative drilled shaft. So if we were to not base isolate the structure at all and design it using conventional methods, this would be the moment demand in that shaft. Second, we base isolate it. Of course, we're going to get a huge reduction in the moments because we're just not shaking it as hard. However, if we then look at what happens if we design with a time history matched to the uniform hazard spectrum there, then we look at what happens when we do the conditional mean spectrum. So we go from maybe 27,000 kip feet to 15 to 20,000 kip feet. So substantial reduction. So this allowed the designer to revise the bridge design substantially. In fact, the shaft size reduced on average from 11 feet to 9 feet, and the reinforcing was reduced by about 1%. The column size was also reduced substantially from about 6.5 feet to 5.5 feet, and that reinforcing was reduced. Also, you can consider some of the softer impacts from that. Sam talked about, scheduling and sequencing and that kind of thing, and how that impacts a contractor's costs. So that was also part of it. But also there's reduced environmental impacts. If you're using less concrete, you have fewer concrete trucks that are clogging the roads, fewer emissions, less cost in terms of emissions to even make the cement that goes into that concrete. And so it's a virtuous cycle. You just keep doing less and less harm to the environment. So we estimate the net savings was about 30 to 40 million to the project when we went to base isolation and CMS design, and that's about 15% of the project cost. So, obviously, base isolation is a very powerful tool to handle very large seismic demands in the right setting. And when we're doing a soil structure interaction analysis, conditional mean spectra can lead to more realistic time histories and a more economical design, especially in a unique seismic setting that is Western Washington, where we have very different types of sources. In California, where you only have crustal sources primarily, you might not see as much of a benefit using CMS. Of course, for any soil structure interaction analysis, it's garbage in, garbage out. You must have an extensive subsurface exploration and testing program in order to have a successful design. And when you get into these complicated analyses, you need to have a very effective communication and coordination between the structural designer, the geotechnical engineer, and the peer reviewer along all the steps of the process. Otherwise, you'll never get anywhere. So I finished a little early, which is nice because I get to show you pretty pictures from the construction. Construction started in late 2014, early 2015, and the bridge opened to traffic in the summer of 2017. So here's an aerial shot of the bridge, and you can see here, this is the construction trestle that was constructed to the north of the existing bridge, and there's these little finger piers that come off. That's where they were able to park their drilled shaft rig and actually construct each pier. This was constructed sequentially, more or less, from Montlake here on the west out, and then also from Foster Island here to the west, and then again to the east. This was supported on 24-inch diameter driven pipe piles. They were vibrated in primarily and then proofed at the end with impact hammer, and there you can see them plucking up one of the piles. Here's an aerial view of the construction trestle. Let's see, easternmost, I believe it was 3 or 4 piers were actually constructed from barges, because out that far into the lake, the water was deep enough that barges were practical. To actually construct the drilled shafts, they had to case through these very soft sediments, these peats and soft clays, down into the glacially overridden soil. So they had 8 to 12 foot diameter steel casings, typically 1 inch thick. They were sacrificial. They were left in place because they had to allow the concrete to cure so that it wouldn't squeeze. These were vibrated in to about 5 feet into glacially overridden soil. The drilled shaft rig. Spills were an ever-present concern during construction as you're reaching down into the shaft and then transferring over and leaving your muck in one particular place. Just gives a sense of scale for how big these drilled shafts are as they set up the rebar cages. And then as they stand and finish from the top. Now here we are actually getting out of the ground a bit. And these are the tops of the columns where the seismic isolation bearings will be placed. And this is a photo of one of those isolation bearings. It's encased in rubber, so you can't actually see those 2 dish plates that I mentioned. But they're there. Next. Aerial view as we near completion. We've got the girders spanning between the piers, and we're moving along. And then the final product. You can go drive it while you're here visiting in Seattle. So thank you for your time, and I'd be happy to entertain any questions with the 3 or 4 minutes I have left. Thank you.
Speak to the microphone if you don't mind, please. There's one right up there.
So I remember when the original bridge was built. So my question is that according to Paul Dorpat's book, Build Washington, which is History of Civil Engineering in the state of Washington, and the Construction Inflation Index, as analyzed by the Associated General Contractors, AGC, that the cost of entitlement for the 520 bridge was more than what the bridge originally cost built after adjusted for inflation, just the entitlement. Why is that?
You are asking the wrong person. I am not qualified to answer that question. To be fair, the environmental concerns are a bit more well understood these days than they were back in the 1960s. Very carefully. Any other questions?
Okay.
All right. Thank you very much.
Thank you, Jeremy. And just to respond to that question, the pendulum for environmental sensitivity has certainly swung, and you're probably raising a relevant issue, but I think that horse is out of the barn and we're not going back, so it's just a new reality. Anyway, well, thank you for attending this session.